today's talk by Nikhilesh Dasgupta, and this is about algebraic characterization of the affine Series space. Please.
So, can I share screen now? I hope the screen is visible to everyone.
Yes.
Please let me know if you can't hear me or something.
We see.
So the title of the talk is, as you know, an algebraic characterization of the affine 3 space. So let me fix up some notations first. For a ring R, and by a ring I will mean a Noetherian ring, and if not Noetherian, at least a commutative ring with unit. In most cases, I will be deal with finitely generated algebras over fields, so the rings will be Noetherian. So square bracket R square bracket n. So if I say B is Rn, it means B is isomorphic to the polynomial algebra in n variables over R. And for most of my cases throughout the talk, A will always be an algebraically closed field of characteristic 0. B, often I will, when I denote B, I will mean an affine K domain. So then I mean that is a finitely generated algebra over the field K and as well as an integral domain. And B star, the group of units. So let's start with a very interesting problem of affine algebraic geometry. It says characterization problem. What does this characterization problems? Yes.
It's visible very bad. It's just for me or for all participants?
No, I see quite good.
Okay, so, sorry.
You can send the file also if you want to some email or something if you want. Is that required?
Maybe you can send files.
Send file to which email?
Okay.
To the chat?
To the chat, maybe.
How to do that? From it has okay, chat. Yes. Just wait me 1 second. File, yes. Yes, I've sent it. Okay.
Thank you. Yes, we see.
Thank you very much. Sorry.
So what does this characterization problem ask? It asks for to tell us to necessary and sufficient conditions on the affine domain B, such that B is a polynomial algebra over K. So, and it is, we will soon see it is closely related to very challenging problems like the Zariski cancellation problem. So finding necessary and sufficient conditions will often help us. But what type of conditions, of what flavor, that totally depends on the context. So first of all, so when I define a polynomial algebra over a field or over any commutative ring, by definition, it means there exists some coordinate system. That means correct number of algebraically independent elements, which generated also as an algebra. So obviously, one necessary and sufficient condition should be that there exists a coordinate system of B consisting of n. But suppose I give someone, B is a finitely generated K algebra, and I give just n algebraically independent elements. First of all, it is not very easy to decide whether they form a coordinate system of B. Obviously, when we know B is like K x1, x2, xn, then we know K x1 up to xn is one set of coordinates. We can apply various types of automorphisms on it to get new sets of coordinates. But suppose given an abstract domain B, how to extract that information? Even when given a single arbitrary polynomial, it is also always not easy to decide whether f is a coordinate. For example, these two cases will tell us how difficult it can be. This is the defining relation for the famous Russell-Korres threefold. As you all know, Makar-Limanov showed that the Makar-Limanov invariant of this is not equal to C and it is generated by Cx. So, and actually he showed that if I go modulo this F, Cxyzt modulo this, that is not isomorphic to C3, and hence obviously then it will not be a coordinate. And that paper involved some little bit new techniques which were not around at that time. Even then, so when we ask, suppose I have Kxyzt mod F to be isomorphic to K3. It's a three-dimensional thing, so it will be isomorphic to K3. Then can then I conclude that it is a coordinate? Well, then also there are candidates like which are open. For example, this is called as a Vennerau type polynomial. There is an entire family of such polynomials where the second x, y plus x, they put an x to the power m. So this is m equal to 1 for this case. For other cases, it has been settled that indeed this f is a coordinate, but the question for m equal to 1 still remains open till today. So it is a hyperplane actually. The references are given here. There's a paper by Bhatwadekar and Datta where they came across this polynomial when they were looking on a polynomial ring in 3 variables over a DVR. And the paper by Lewis, more recently, he took it as a polynomial in 4 variables. And he proved that along with x, it is a CX hyperplane basically. So if I view it as a CX YZT algebra, so it is of the correct dimension modulo that. But it is not still yet not known that whether it is a coordinate or not. And these are, you can see, yt plus z square, these things, these are somewhat related to the exponential automorphism. So decide, given an arbitrary polynomial, my point is it's not very easy to decide on. So what can we expect?
Power m, Nikhilesh?
Yes?
X to the power m greater than 1, it is known, is it?
It is known it is a coordinate. M equal to 2 was unresolved for a long time, but m equal to 2 also Lewis has solved actually in this paper. The reference is given. But for m equal to 1, it is not. And actually, the example given by Bhatwadekar and Datta, they took up the case for m equal to 1 only. They didn't consider the entire family of polynomials. So x was that uniformizing parameter for the DVR, like that. So some necessary conditions without going into coordinates and coordinate systems. What should we expect? If we say some B to be a polynomial algebra over K, so obviously it has to be a UFD. Units should be trivial. It should be a regular ring. You can say the modulo of differentials should be a free module over B. And even if you want to look at it topologically, over C, the spec B should be contractible. But one may ask, are these also sufficient? Well, for low dimensions, not all of these information may be required. For example, if I take, suppose n equal to 1, that means dimension B is 1. So I have got a one-dimensional domain over an algebraically closed field of characteristics here. Then only, yes?
What does it mean B is regular?
Regular, I mean, it is at every prime, if I localize at a prime ideal, it is a regular local ring.
Okay.
Or the maximal ideal has the correct number of generators. Or you can say m mod m square has the dimension of that ring after localization.
Okay, thank you.
Smooth, if you wish.
I'm sorry, and what does it mean contractible?
Contractible, I mean contractible that homology vanishes, and that in that sense, if you take the homology as a manifold.
Thank you.
No, contractible means that it can be contracted to a point, right? In a topological sense.
So it contracted to a point is a topology. So the fundamental group will be that of the point also.
No, but in terms of topology or fundamental group, this is only sufficient but not necessary condition, right?
Yes. Yes.
It should be contractible to a point.
Yes.
So this is
yes.
In Russian, this is стягиваемое.
Okay. So I'm proceeding. Okay. So suppose n is 1 and dimension B is 1. So this is a purely algebraic characterization. So B is K1, if and only if B is a UFD with trivial points. This is a result by one can find in the papers of Abhyankar, Ikin, and Heinzer, and some trivial stuff one can show that. And this was a well-known topological characterization also, that if it is K is C, that the affine line is only the acyclic. Actually, acyclic means the homologies are trivial. Acyclic normal curve. But for now, I will be worried mostly with the algebraic characterizations, and that is main the target of my talk. So for n equal to 1, it is nothing much. Well, for n equal to 2 and dimension 2, the first topological characterization or even the characterization of the affine plane was given by C.P. Ramanujam in 1971. What he proved is X is a smooth affine algebraic surface over C. Then X is isomorphic to C2. If it is topologically contractible, what I said in that sense, topologically contractible, and not only the fundamental group at infinity also has to be trivial. It's something more. In 1975, Neena came up with an algebraic characterization that B is isomorphic to K2 if and only if. So obviously you should expect that UFD and trivial units should be there. Now he says spec B contains a cylinder-like open set U cross A1. In our language of commutative algebra, this is same as saying that there exists a subalgebra A of B and an element F which is an A, such that if I localize with the multiplicative set F to the power n, BF is AF1. Well, this is, if you are familiar with the language of local nilpotent derivations, this is just saying there exists a non-zero LND. Because the non-zero LND will come with local slices. And if you localize at the correct element, you will have a slice-like thing, and this will happen. I will soon go into those details gradually. So, a major application of, yes.
Returning to topological characterization. And what is the fundamental group at infinity for a sum?
It is actually, they take the limit of, they take of the complement of the compact sets and compute the fundamental group.
Okay, I see.
Excuse me, is it enough to add just one point at infinity and compute the fundamental group here, or is this a different concept?
So you are asking if I just say the fundamental group is trivial, and will that be sufficient?
Yeah, no, I mean, if this P1 at infinity, is it enough to add just one point or not at infinity?
I think so, because these spaces will be path connected also.
Okay, thank you.
But what I know is in Ramanujam's paper, he gave certain examples where he showed that topologically contractible spaces, they were smooth, and the fundamental groups were trivial, but not the one at infinity. And this actually brought into this factor into play.
Thank you.
Okay. So Miyanishi's characterization is this. So let's apply these two to see how it helps in solving the Zariski constellation problem for n equal to, for n less or equal to. So suppose B1, so let's state the problem. Question is very simple. I have got an affine K domain. I know stably it's a polynomial ring in n plus 1 variables over K, that is B1 equals to Kn plus 1. Will it imply that B is Kn? So for n equal to 1, it becomes B1 equals to K2. Well, immediately you can see if B1 is K2, then B1 is a UFD, so B will be a UFD. And since B1 is K2, the units of B also will be trivial. So if we use our algebraic characterization for dimension 1, we immediately get that B is K1. And Miyanishi's characterization was used to show that the answer is affirmative for n equal to 2 by Miyanishi Sugi in 1980 and independently by Fujita in 1979. But for n greater or equal to 3, in characteristic 0, the answer remains open. And for positive characteristics, Neena Gupta in 2014 gave an example for by the Asanuma's threefold, where she showed that B1 will be equal to K4 and B will not be isomorphic to K3. So for positive characteristic, answer is false, and for characteristic 0, the question remains open. And there are lots of candidate counter examples. So coming to n equal to 3 and dimension B equals to 3. This is a result by Kaliman in 2002. Though in literature I find there are results by Miyanishi also, of the same flavor, but this is the final result which I see from Kalimanov, that it is a affine algebraic variety of dimension 3 now. So UFDC's trivial units are there. The third homology group H3 with the coefficients in Z vanishes. And instead of saying X has a cylinder-like open set U cross A1, he says X contains a cylinder-like open set U cross A2, such that the irreducible component has singularities which are at most isolated, X minus Q cross A. Well, this time when I will show you our characterization of the affine 3 space, we will have at some point that given that affine domain of dimension 3, we will have some subalgebra R inside B such that B is equal to R2 under certain conditions. I do not know whether this condition is directly related to that or not. I read the paper, but I could not see this result entire algebraically, apart from going into a little bit of topology. So I wish there was a complete algebraic proof of this result. At least it was not beyond my reach. It was beyond my reach to see. So now let's start with local and nilpotent derivation. So this is the up to dimension 3. We have given some algebraic characterizations. I will say not algebraic, algebra topology, because there's some way little bit algebraic, little bit topology. So these are basics. I think most of you are familiar with it, but I will go through them one again. A K-linear map D, B to B is called a derivation if it satisfies the Leibniz rule. In addition to it, it is said to be local and nilpotent if for each B their existence such that d to the power nb is 0. And LNDB, I will denote the set of all local and nilpotent derivations of B. Kernel is the set of elements of B which go to 0, dA is 0. And these are two important properties of the kernel. It is always factorially closed. What do I mean by factorially closed? That if product of two elements are in kernel D, individually the elements also will be. And factorially closed actually imply algebraically closed also. And that is at many cases needed to show something precisely is the kernel. In many cases, when we compute the kernel, we can find out certain polynomials or certain candidates which are already there. But how to show kernel D is the precise algebra generated by that? Then we have to compare the transcendence degrees, and using the fact that it is algebraically closed, we have an equality. And always transcendence degree of B over kernel D is 1. So this is another interesting question, but we are also not in this direction right now, but still I will say something on this. So if B is affine, one may ask, is kernel D always affine? So in the language of commutative algebra again, is kernel D always finitely generated as a K algebra? Well, even for polynomial rings, it is yes, if, so there is a typo here. It should be N, I think I should make the, is less, and if N is more than 5, there are examples by Daigle and Freudenberg which show the kernel is not finitely generated, and the only case remains is N equal to 4. And under certain hypotheses, there was a result by Patwadecker and Daigle who showed that kernel D indeed is finitely generated, provided it contains at least one coordinate. So if I do not assume that, there is no known result which directly says that the kernel D, whether it's affine or it is not finitely generated. So, as you all know, there is also well-known one-to-one correspondence between LNDB and the regular G actions on spec B. And affine K domain will be defined to be rigid if it does not have any non-zero local and nilpotent derivation. And I define another term which is almost rigid if there is only one non-zero local and nilpotent derivation and every other local and nilpotent derivation is a multiple of. So multiples of what? We take something from the kernel and we take FD. It's easy to check that FD is indeed a local and nilpotent derivation. The Makar-Limanov invariant of B is defined to be intersection of all the LNDs of the kernels of the LNDs. And one can immediately easily check that. For polynomial ring, we have the Makar-Limanov invariant to be trivial. And as well as for a rigid ring, it has to be the whole ring. So these are like the two extreme cases.
Excuse me?
Sure.
May I ask about the almost rigid definition? Yes. There is sometimes a situation when all derivations differ by multiple by some function, but
Oh, you mean whether the
LND is not
derivation is
generated by, well, when you can always say that two derivations obtained by multiplying on functions from the kernel, but there is no such derivation which generates all the LNDs. Maybe there are two which are equivalent, but
they are equivalent.
they generate everything else.
Yes.
Total.
They are
So,
proportional by rational function.
yes, which are proportional by a rational function, and there is no unique derivation which generates everything with regular functions.
Is it possible
So,
for
would you like to call them almost rigid as well or not?
Yes, because if they differ by an element of the kernel only, so you are saying maybe D1 is equal to some lambda D2. The lambda is from kernel D1.
But the question is, there are two definitions. The first is as you give, and the second is that all kernels of all LNDs are coincide. And not all varieties which are almost rigid by the second definition are
Okay, so I am using this definition actually.
this definition.
Okay, thank you. I just wanted to clarify.
Yes,
Thank you.
yes, it's nice to know that thing. So next is locally nilpotent derivations with slices. Why do I do this? Because the new invariant which I will define will involve some special type of locally nilpotent derivations. Any D in LNDP is said to have a slice, and if just that is as simple that is that there is some element S such that it sends it to 1. Actually, instead of 1, you can say DS is in B star also. Unit in B, basically that means. And it means that the GA action is equivalently trivial. It looks like a translation. This is an important theorem, or a very easy theorem, but a very well-known theorem. You can find it in Freudenberg's book. The reference is also given. So if what happens if D, LND has a slice. So let D is an LND with a slice and A is the kernel. Then B becomes a polynomial ring over A. So B is A1. And you can say B is like the partial derivative with respect to S. A is pi S of B. This pi S is the map which I'm defined. Pi S is called the Dixmuir map. It sends any element of B to A. Dixmuir map actually over a field of characteristic 0 can define for any non-zero LND. This is a special case of the Dixmuir map. Using local slices, one defines Dixmuir. So it says the image of the Dixmuir map is exactly equal to the kernel. This map generally need not be surjective. Here it is surjective if there is a slice. And this is one way we find out actually the generators of the kernel also. And also if B is affine, then Y is affine because Y will be a quotient of B mod SB will be Y. But never I am saying that. If I say B is AS and suppose whether S is a coordinate in B and like thing like that. Actually, one can show the slice will be a stable coordinate. But one needs more assumptions to say on A and stuff like that to see whether S is a coordinate, if B is AM. So consider this subset of the set of locally nilpotent derivations. So I involve only those derivations which have slices. Again, their kernels also will be algebraically closed, subalgebras, and I can take the intersection. I define that invariant to be ML star. Honestly, I should not say I define it. I found it in the last section, in the previous version, and I gave it I just called it at that time Freudenberg Makar-Limanov invariant, and then I think someone suggested let's put it ML star. So the idea is not entirely by me. It is I found it from Freudenberg's book that one can construct this kind of invariant. But obviously we will see there are affine domains where there is no local nilpotent derivation with a slice. Even there will be domains where maybe it like almost rigid ones, like I defined, there might not be derivations with slices. In that case, I will define ML star B to be B, because this set there will be then M. So, few results. The ML star of the polynomial ring, you can see same as the Makar-Limanov invariant of the polynomial ring, and it is equal to K. The partial derivatives indeed are have slices. Also, you can see MLB should be contained in ML star B because it is a intersection over a slightly bigger. MLB is an intersection over a bigger family, so MLB is small. But it can be a proper subset also. It can be a proper subset. And so what one should expect? Suppose I have a ring A domain B and I add a coordinate B1. Every derivation of B, I can extend it trivially to a derivation of B1. So if I consider all the local and nilpotent derivations of B1, there are already some which have been extended from B, and there might be others also. So generally, ML of B1 should be smaller than ML of B. ML star of B1 should be smaller than ML star of B. But in our paper, we could show that actually ML star of B1, you can say it is contained in MLB. See, MLB is contained in ML star B also. So this is also smaller than MLB. So dimension, let's come to characterizations now. In terms of the Makar-Limanov invariant.
I'm sorry.
Yes.
Can I it is not true that ML star of B1 equals to ML star of B.
No.
It's not true.
Not always.
Okay.
Not always.
Thank you.
So this is a result by Crashiola and Makar-Limanov 2005. It says, so B dimension B is 1, algebraically closed field always a characteristic 0. That B is K1 if and only if the Makar-Limanov invariant is trivial. In other words, if there is some non-zero LNE on it, it has to be K1. Obviously, if I want to extend this and check whether this is true in dimension 2, I will fail. In dimension 2, the Danielsky surface serve us as examples where MLB is K, but B is not K. So I consider this family X, Y, Z, X to the power NZ minus PY, where you can say degree of, if N is 1 or degree of PY is 1, then MLB will be K. But degree of PY equal to 1, we are not bothered because that makes it a coordinate. So XZ minus PY. For those kind of varieties, the Makar-Limanov invariant will be trivial, but obviously these are not UFDs. So they can never be equal to K. And just a remark, if N is more than 2 and degree of PY is also more than 2, MLB is equal to KX. Essentially, there is only one type of a local and important derivation, which annihilates also X. So okay, let's come to our result. This is our first result, characterization of K. So B is an affine K domain such that dimension B is 2. Then we have following to be equivalent. That B is polynomial ring, ML star B is K, ML B is K, and ML star B is not equal to B. So basically, we only assuming MLB equals to K by the previous discussion, you can see is not sufficient. So one also has to assume that it has at least one local and important derivation with a slice. And this 3 will imply 2, and essentially it will mean that ML star B will be K. The remark is, yes, okay. The remark is, see, why I was so excited with this result is, in Mianish's characterization, if you remember, always there was an assumption of an UFD. Here we do not even require it to be a UFD or certain with trivial units and stuff like that. Only assuming that ML star B is K on an affine domain with dimension 2 gives us the fact that B is K. And if one goes through the proof of this theorem very carefully, we can see that this K is algebraically closed. This thing can be dropped. What you need to assume that K is algebraically closed in B only. And it will not hold also. Unfortunately, this result will not hold if I move one dimension more, or dimension 3. There we have to assume that B is a UFD, then similar result will again be true. No result regarding homology or the fundamental group or some, as I say, cylinder-like open sets in that language will be needed. So let's see. This is an example for, you can see, kxyz xy minus z square minus 1. And I consider the polynomial ring over this R. So it is a three-dimensional domain. If K is an algebraically closed field, which we are now considering, B is not a UFD. So one thing for sure, B can't be equal to K3. But MLB and ML star B, one can show that they are equal to K. And even this ML star of R is R. So R is actually essentially a rigid ring. And B is isomorphic to K3. So this is one example which we showed that our theorem will be true if we do not assume that UFD thing. So while proving the fact on the characterizations of K3, we came up with this first result. So now from now, B will be an affine K domain, which is a UFD and dimension is 3. So even if I write B, I'm assuming it is a UFD. If I can show that it admits only two non-zero distinct local and nilpotent derivations with slices, then there will exist a K subalgebra R of B such that B can be shown to be R. Now, this result actually gives you the characterization essentially. This is the crux of this thing. If I have some way I can show there is B is equal to R2 and R is not rigid, it means the Makar-Limanov invariant is trivial. Then by the characterization of Cracciola and Makar-Limanov, you can conclude that R will be K1 by comparing the transcendence degree of R will be 1. And if R is not rigid, then obviously R will be K1. And if we should get our answer. I will also give you an example. Again, if I increase the dimension one more, if I take a 4-dimensional UFD, this result will again not be true. So there actually we will show there exists no subalgebra like that. So this is one proposition which was needed to prove our theorem. So it talks out the different cases. That's why I included this. So first of all, I assume, suppose MLB is equal to ML star. Well, immediately you may ask me, that is a very important question. How do you know that? Well, suppose I assume this. So one question is there, for which rings or which affine domains of certain dimension can we say that MLB is equal to ML star B? Well, that is one matter I will come to. But for now, suppose MLB is equal to ML star. So because if you see, when I assume ML star B is K, automatically MLB, which is sitting inside ML star B, that also will be. So MLB equals to ML star B, that hypothesis will be satisfied. So if transcendence degree of MLB is 3, obviously B is rigid because B is a 3-dimensional. If transcendence degree of MLB is 2, then there exists an affine K subalgebra C of B such that C is rigid, C is a UFD and B is C1. So it's like there is only one type of local and nilpotent derivative. And if it is 1, there exists a K subalgebra S of B such that S is rigid, S is a UFD and B is S2. Moreover, there exists a T that S has got units which are not trivial basically. So it is KT 1 by PT, where PT is a non-constant polynomial. So in particular, you can say units of B star, that means the units of B are strictly bigger than the non-zero elements of it. And if transcendence degree of MLB is 0, that means MLB equals to K. If K is algebraically closed, then B is equals to K. But for that, you remember, we include this hypothesis that MLB is ML star. So how can we conclude that MLB is ML star? This is one result. I will come to it again later. That if I know there is only one local and nilpotent derivation with a slice, that is enough to assume that MLB is equal to ML star. So, and this is our theorem, which gives the characterization of K3, that B is isomorphic to K3, if and only if ML star B is K, MLB is K, and ML star B equals to B. I also mentioned here, though B was a UFD earlier, it means that B is UFD. That was a blanket assumption for this part of my discussion. So, two remarks here. In lemma, the hypothesis that ML star B not equal to B. So let's go to lemma 2. Lemma 2 says, if there is a local and nilpotent derivation with a slice, then these two invariants have to be equal. So this hypothesis is necessary, we will see. I will show you examples of 3-dimensional affine UFDs such that there will be no local and nilpotent derivation with a slice, but we will have all possible scenarios of the transcendence degree of MLB. It is 0, it may be 1, it may be 2. And so obviously ML star B will not be equal to ML. And our characterization, this thing, also does not translate to a higher dimension. That one example also I will discuss. So let's come with the examples first. So this is, we are considering MLB is K, that the transcendence degree of MLB is 0, but ML star B is equal to. This is the ring. KXYZT modulo XY minus ZT minus 1. You can check by Nagata's criteria, like inverting X or something, that it is a UFD. It is also regular. One can also check. Regular means smooth, if you ask me. And MLB is K. For this, we consider 4 non-zero local and nilpotent derivations. These are given here. You can alternately send X to 0 and Y to 0 and do the other part with Z and T. And if you compute the kernels, it will be some XZ, YZ, XT like that, and you take the intersection. Intersection will be K, and since K, it has to be at least K, it is equal to. So this is generally a technique through which I compute MLB or even ML star. I pick up special local and nilpotent derivation. I construct them in such a way that taking the intersection with the kernel, the transcendence degree keeps on dropping. And I drop it down to the least possible. But this is not K3 because the weighted group is not trivial. X, Y, Z, T. You can map it to a invertible matrix, but not elementary. So ML star will be B will be equal to. Now let's come to the Russell chorus. This gives a scenario, as you all know, the Makar-Limanov invariant of the Russell chorus threefold is CX. But I will also show that ML star B is equal to B. So B is a UFD that is well known. MLB is CX, that is also well known. And actually transcendence degree of MLB is 1. And by the proposition, I can say MLB cannot be equal to ML star. Why? Because had it been the scenario, let's go back to the proposition. If transcendence degree of MLB is 1, then there is a S such that S is like KT 1 by PT. That means K star is a strictly smaller than the units. So here, if I look at the Russell chorus threefold, it has trivial units. So it can't be MLB can't be equal to ML star. And so ML star B equals to B by that. The only remaining case to show is ML star B equals to B and transcendence degree of MLB is 2. I take this rigid ring and I construct B like RUV X square U minus Y cube V minus 1. It will be an almost rigid in my sense, what I said, only one type of local and nilpotent derivation and everything is a multiple of it. Dimension 3, it was proved by Princeton and Mobach that MLB is equal to R. ML of this being is equal to R. But you can see clearly B is not a polynomial ring over R. So ML star B is equal to. And transcendence degree of MLB is also. Okay. This is the example of that XYZT minus 1 where the MLB was K but ML star B was B. I use this to show our characterization does not extend to dimension 4. So I take this ring, I just extend it by a variable. So now it becomes BU, B tilde becomes a 4-dimensional unit. Smoothness and regularity will be preserved. Also, one can show that ML star of B tilde and ML of B tilde are equal to K, and B tilde will not be isomorphic to K4. So again, I extend those local and nilpotent derivations, which I constructed there by making them to have slices. So see, initially I didn't have slices. If I go back to that example again, D1, D2, D3, D4, none of them have a slice yet. I extend it not trivially in that sense. I extend it by setting the extra variable to be 1. So now I can include them in computation of ML star. And I take the usual partial derivative with respect to what the intersection will come. The calculations are here, if you can check. So intersection finally will be equal to. And since in ML star B has to be K, then MLB tilde also K. But as you know, the weighted group of B was not trivial, so K1 of B tilde is also not K star. So B tilde also can't be equal to K4. So it is very interesting to think what extra condition we need to assume in that theorem. We already assume it is UFD. We are assuming ML star is trivial. And so
Nikhilesh, so we have difficulty with voice. Please come to the dynamic.
yes. Can you hear me now?
Now it's okay.
No. Yes, now we do.
Okay. Just let me know if I'm inaudible. Okay. So I'm saying it's very interesting to think what extra condition we need to assume. We assume that the domain, our domain is a UFD. We assume that there are sufficient local and nilpotent derivations with slices that the Makar-Limanov invariant is trivial. And for dimension 3, it seemed to go through. But maybe something on the other types of derivations or something, I do not know, maybe some other invariant. In terms of this, I mean, to classify polynomial rings or give a good characterization. This is one lemma, which example 6, which I think I can skip. You can find out. It shows that the lemma 1, which I should ML star be not equal to B, implying that MLB is equal to ML star B, does not hold. Just I will state it. Take Rx, Y, Z to be this. This is a rigid thing. And instead of X square U, Y cube V, the example we constructed, we take C to be RUV mod XU minus YV minus. And we have what we will have UFD of dimension 4. We can show that ML and ML star B are both R. B will also not be a polynomial algebra over R. In fact, B is not equal to S2 for any case of algebra. So those things will not go through. So I skip this example. What I'm interested in this question also. So given an n-dimensional affine domain B, we know what we know for now is MLB equals to ML star B holds when transcendence degree of ML star B is n minus 1 for any n greater or equal to. This has been proved in our paper. This is lemma 3.2. We know that MLB equals to ML star B if dimension B is equal to 2 and ML star B is not equal to. Also, we know when dimension B is 3, ML star B is not equal to B and B is a UFD. So keeping these results in mind, I have a question and I could not find an example for it. Does there exist a three-dimensional affine domain, obviously which is not a UFD, such that MLB is K, but transcendence degree of ML star B is 1? I could not find. Because you see, if transcendence degree of ML star B is 2, 3 minus 1 is 2. So by our result, that then MLB will be equal to ML star. So, and obviously if MLB is K and transcendence degree of ML star B is 1, MLB is not equal to ML star. So this is one example I could not find. And another question is regarding this Russell Chorus 3. So Makar-Limanov showed that this was a candidate to the linearization problem, which for a counter example to the linearization problem is not isomorphic to C3 by proving that the Makar-Limanov invariant is not trivial. So we already know it is not isomorphic to C3. If B1 is isomorphic to C4, then this will give a negative solution to the Zariski cancellation problem in characteristic 0. Well, there are a lot of works down that line, but I am not very much familiar with the methods of Dubolos and Fazal who use A1 homotopy. Actually, Dubolos, this result was a little bit algebraic. He constructed derivations and automorphisms to show that the cylinder over this M of B1, this is C. But it is a 4-dimensional thing. You cannot conclude that MLB1 is C implies that B1 is C4. And Dubolos and Fazala also have shown that this is A1 contractible in the sense of A1 homotopy. From our result, what we can deduce is ML star of B2 by the result will be contained in ML of B1. By Dubolos' result, MLB1 is C. So ML star B2 is equal to C. So at least for n greater or equal to 2, we have ML star of Bn is equal to C. So I was also even investigating this problem. Is ML star of B1 equals to C? If not, obviously then B1 can't be equal to C4. But to construct a local and nilpotent derivation with a slice on B1 was not easy for me. So I do not know, apart from constructing LNDs like that, is there any other way to even answer this question, is ML star of B1 is. So I think I should stop with this, and the rest is bibliography, though not in an alphabetical order. So I am very happy for any questions or comments you want to make.
I have no any questions, but I want to say that that was very interesting for me, and
Thank you so much.
I just have a big so I want to read your paper.
I will say it. Just stop sharing for now. I will send you.
Nikhilesh, may I ask you before you stop sharing, just to demonstrate us list of reference? This is very interesting.
Oh, sure. I will do that. So they are not in alphabetical order, but this is the paper of Rashiola Makar-Limanov. This is, I have not got the DOI yet. I do not know why, but it has been accepted at Journal of Commutative Algebra. I will send you the paper. Finston Morbach, and this is the Fujita paper, the paper of Kaliman, Makar-Limanov, Miyanishi. This is Neena Gupta's paper on the Z set, he says the Zariski's cancellation problem, and the papers of Dubolos and Fuzzle. And if somebody is interested also, this is on the Venero type polynomials, which I said in the beginning, the paper of Lewis. And obviously, I should not miss out on Freudenberg's book. That has been a vast research for.
There is a conference for Kaliman this year.
Yeah.
And number 2, is it available on Archive?
It is available on Archive, but I think we have a little bit updated version of it. So you can check the version at Archive. I think so it is updated, but I will send you both if you want. So you can download it from Archive, but I can send you my copy also.
Okay, thank you.
And it was
See,
a
there
remark,
are certain remarks I want to say. For example, the questions which I said on Russell-Kurus threefold, not that much detail might be there. I've added some little bits and bits there, but the basic idea and the results and all the proofs and the examples are there. That is for sure.
Sasha was going to say something, right?
Yes,
No,
go ahead.
I just want to say that I will be grateful for the paper, that's all.
You have read this paper
I
before?
would be grateful for your paper, for your article, if you send it.
Okay, you want to read?
Yeah.
Yes, I will definitely send you. So, is there a common email ID so that anyone interested can access it, or shall I send it to you, sir? Azazdev, sir, I can send it to him directly. Or you can have my email ID, or also that will be also be better. You can approach me anytime with any questions regarding if you have anything while reading the paper.
Sure. I sent my email to chat.
Sure.
So.
And mine too.
Sure.
We will share the paper with other people here.
Also can share, yes.
If you don't mind.
Can I send the file also in this chat? Then you can download it right now.
Yes,
that will be better.
Perfect.
Why postpone it for later?
Yeah.
I have it ready. Just one second.
Such a nice notion, Makar-Limanov invariant. So many variation on this. Today we had ML star. Also, there is some field Makar-Limanov invariant and so on.
Yes, FML. Yes. And also, I think there one can do with the homogeneous local and nilpotent derivations also.
Yes.
You take the intersection of the kernels of the homogeneous local and nilpotent derivations. Also, if you can take the kernels of the fixed point field local and nilpotent derivations. So it's interesting when they all coincide or how they vary.
Okay, and I heard some words about Makar-Limanov, about the conference dedicated to Kaliman, which is planned for this summer in St. Petersburg. Now the situation is not completely clear because of this epidemic situation, pandemia. So I am one of the organizers of this conference, and we decided to make a final decision at the end of March. So this is our interior deadline, and we will decide whether it will be in a standard way. We will invite guests to St. Petersburg, or we'll look for other format. So final decision will be at the end of March.
Thank you.
Send the file. You can download it.
Okay, thank you much.
PML_JCA.
Dear colleagues, are any other comments, questions? Discussion is very welcome. Such a precise results, so and such a nice presentation and clear talk. So
thank you, sir.
People understand.
Yeah, prerequisites are not that much for this result.
I don't know if it's possible to think about it from geometric viewpoint, because this ML star, it is, I don't know, intersection of, in geometric way, can you characterize ML star or not?
You mean in terms of vector fields and things like that?
Not precisely. It seems that if I have an LND with a slice, then my variety is the spectrum of this algebra is just a cylinder. Yes, it is line multiplied by some other variety. Yes.
Okay.
And something like this, I don't know what kind of results can you say geometrically, but is there some geometrical results?
There should be. This is not a very new concept of local and important derivation with a slice. Generally, through my background, I generally looked at it in more algebraic point of view, the view of commutative algebra. Not much of a geometry, but I think there are certain results by Freudenberg which says, if, for example, you take Rxyz, where R is a Dedekind domain or some nice small dimensional object, and you have a local and nilpotent derivation with a slice on R, and suppose A is the kernel, then R is an A2 fibration over it. So results are like that. So there are like fibrations. You can ask whether the general fibers are polynomial rings with the correct dimension over the kernel. Those kinds of results are there.
Sorry, and another question.
Yes.
If I have a derivation,
yes.
Is there an algorithm to say if this derivation, if this LND has a slice?
Well, that might not be easy to say. At least for me. You give me an LND on an affine domain, I just want to check whether it has got a slice or not. But when it is not very obvious that it is not a cylinder over some subalgebra and stuff like that. Even just an LND, it needs some computation, might be, because that is way I got stuck with this Russell Chorus threefold. That problem.
Okay.
Because if the number of variables are a little bit more for maybe low dimension for kxy or kxyz, I think one can do it easily. But when it becomes at least 4 variables, it becomes difficult to compute. Because ds simply means it's like an unimodular row. So what should be that, so that fx into dx plus fy into dy, that should be 1. So there are so many possibilities. Given something is very easy to check with a slice, and maybe for certain special cases one can do. I had another research work during my doctorate, which was based on nice derivations, something called as nice derivations. Nice derivations are things where d2 of the generators go xi is 0. So I consider Rx1, x2, xn, polynomial algebra over a PID or a UFD, and I construct those local and nilpotent derivations, which d2 xi is. So it's like dxi is in the kernel. Well, for those cases, it is a little bit easier to check because you do not have to go to higher powers of t. So for an arbitrary derivation, it might be. Actually, after I sent the abstract, I felt I should have combined this talk into 2 parts. That talk also I should have included, making this a little bit shorter. But maybe sometime later, if you have the opportunity, I can lecture on that.
Okay, thank you very much. If there are no more questions, then I just would like to thank Nikhilesh once more and say that I'm very happy that today we have foreign non-Russian guests, participants of our seminar. And I would like to announce that after this talk, we will have at least 3 more talks by our foreign guests. So please follow our schedule, look to our webpage, and you are welcome to next seminars.
Thank you, sir.
So thank you very much. Let me say goodbye to all of you.